Here's a one-shot revision of nuclear physics for Class 12 boards in English. This summary covers all key concepts, formulas, and important points you need to score well. Nucleus. Central part of the atom containing protons and neutrons, nucleons. Atomic number, Z, number of protons. Mass number, A, number of protons plus neutrons. A equals Z plus N. Isotopes, same Z, different A. Isobars, same A, different Z. Isotones, same number of neutrons. N. Nuclear radius, RR equals R0 A to the power of 1/3, where R0 is approximately 1.2 times 10 to the power of minus 15 meters. Density, ρ, is the mass of the nucleus divided by the volume of the nucleus. Approximately 2.3 times 10 to the power of 17 kilograms per cubic meter. Einstein's equation E equals mc squared. Delta M is the difference between Z times mp plus N times Mn and the mass of the nucleus. Binding energy Be is delta M times 931.5 MeV. Binding energy per nucleon is maximum for iron, making it the most stable element. Radioactive decay law. N equals N0 E to the power of minus lambda T, which represents the remaining nuclei after time T. Lambda is the decay constant. Half-life, T1/2, is the time for half the radioactive nuclei to decay, given by T1/2 equals 0.693 divided by lambda. Mean life tau is 1 over lambda. Alpha decay, symbolized as alpha, involves the release of an alpha particle. The equation is Z2 circumflex A4 Y plus underscore 2 circumflex 4 He. Next we have beta minus decay, also known as electron emission. The process is Z plus 1 circumflex AY plus an electron and an electron antineutrino. In beta plus decay or positron emission we have Z1 circumflex AY plus a positron and an electron neutrino. Lastly, there's gamma decay, where underscore Z circumflex AX in an excited state transforms into underscore Z circumflex AX plus a gamma photon. Nuclear fission occurs when a heavy nucleus splits into two lighter nuclei, releasing energy and neutrons. For instance, 56 circumflex 141 bar plus underscore 36 circumflex 92 Kr plus 3 neutrons and energy. On the other hand, nuclear fusion involves two light nuclei combining to form a heavier nucleus, accompanied by the release of energy. An example is underscore 1 circumflex 2 H plus underscore 1 circumflex 3 H transforms into underscore 2 circumflex 4 E plus a neutron and energy. Nuclear physics has various applications. For instance, nuclear power generation relies on fission reactors. In archaeology, carbon dating, specifically C14 dating, helps determine the age of artifacts. In medicine, techniques like radiotherapy and PET scans utilize nuclear physics principles. Lastly, nuclear weapons, both fission and fusion bombs, are also applications of nuclear physics. Always write SI units. Use proper nuclear symbols like X, A, and Z. For numericals, focus on B, decay law, and half-life calculations. Be precise with definitions, especially for mass defect, binding energy, and decay laws. For diagram-based questions, know the nuclear reactor schematic and fusion processes in the Sun. Question: calculate the energy equivalent of 1 AMU. Solution: 1 AMU is equal to 1.66 times 10 to the power of negative 27 kilograms. Using the equation E equals max squared, we get E equals 1.66 times 10 to the power of negative 27, multiplied by 3 times 10 to the power of 8 squared. So E is approximately 931.5 MeV. Start answers with a definition or law. Write formulas before solving numericals. Label all diagrams. And don't forget to revise decay series and fusion or fission equations. The nucleus is composed of protons and neutrons. Protons, denoted as P, are positively charged particles with a charge of plus E and a mass of approximately 1 atomic mass unit, or AMU. Neutrons, symbolized as N, are neutral particles, also with a mass of about 1 mu. Together, these particles are referred to as nucleons. The size of the nucleus was experimentally determined by Rutherford's scattering experiment. The formula for the radius of the nucleus is given by R equals R0 times A to the power of 1/3, where R0 is approximately between 1.1 and 1.2 times 10 to the negative 15th meters. The density of the nucleus is quite remarkable. Since nuclear density is constant and independent of A, it can be expressed as RAO approximately 2.3 times 10 to the 17th kilograms per cubic meter. Let's talk about mass defect, denoted as delta M. The actual mass of the nucleus is less than the sum of the individual masses of protons and neutrons. The formula for mass defect is delta M equals the quantity of Z times MP plus the quantity of A minus Z times Mn minus the mass of the nucleus. Now, moving on to binding energy, abbreviated as B. Binding energy is the energy required to break a nucleus into free nucleons. According to Einstein's relation, energy E equals delta M times C squared. One atomic mass unit, or AMU, is equivalent to 931.5 mega-electron volts of energy. Binding energy per nucleon, or B divided by A, is the average energy per nucleon. Nuclei that are lighter than iron-56 undergo fusion, while those that are heavier undergo fission to achieve stability. The strongest force in nature, even stronger than gravitational and electromagnetic forces, it has some unique properties. First, it's a short-range force, effective only within a very limited distance. Second, it's charge-independent, meaning it doesn't matter what charge the particles have. Another interesting property is its saturation. Each nucleon interacts only with its nearest neighbors. Lastly, this force is attractive at longer distances, but becomes repulsive when particles get extremely close to each other. Let's discuss the types of radioactive decay. First, we have alpha decay, where a nucleus loses an alpha particle. The equation for this is a nucleus of element X transforms into a nucleus of element Y and an alpha particle. Second, there's beta decay. In B decay, a neutron transforms into a proton, an electron, and an antineutrino. The equation for this process is a nucleus of element X transforms into a nucleus of element Y, an electron, and an antineutrino. There's also B plus decay, where a proton transforms into a neutron, a positron, and a neutrino. The equation is a nucleus of element X transforms into a nucleus of element Y, a positron, and a neutrino. Lastly, we have gamma decay. Here, energy is released without changing the atomic number or mass number. The equation is an excited nucleus of element X transforms into a stable nucleus of element X and a gamma photon. The radioactive decay law can be expressed with the equation N equals N naught times e to the power of negative lambda t. The half-life, which is the time required for half of the radioactive nuclei to decay, is given by the formula T 1/2 equals 0.693 divided by lambda. The mean lifetime is represented as tau equals 1 divided by lambda. When we graph this, we get an exponential decay curve showing the number of undecayed nuclei decreasing over time. Nuclear fission is a process where a heavy nucleus splits into two lighter nuclei, releasing energy and neutrons. For example, uranium-235, when bombarded with a neutron, splits into barium-141 and krypton-92, along with 3 neutrons and a significant amount of energy. The reaction can be represented as uranium-235 plus a neutron yields barium-141, krypton-92, 3 neutrons, and energy. Nuclear fusion, on the other hand, involves 2 light nuclei combining to form a heavier nucleus, releasing tremendous energy in the process. A prime example of this is the fusion that powers the Sun. In the Sun, hydrogen nuclei fuse to form helium, positrons, and neutrinos. This reaction can be represented as hydrogen plus hydrogen yields deuterium, a positron, and a neutrino. Fusion occurs naturally in stars, producing the immense energy that powers them. Let's tackle a sample numerical question. Suppose a nucleus has a mass of 7.0160 atomic mass units. We need to calculate its binding energy per nucleon. Given the atomic masses of protons and neutrons, we start by calculating the mass defect. The mass defect is the difference between the sum of the individual masses of protons and neutrons and the actual mass of the nucleus. Using the formula, we find the mass defect is equal to 3 times 1.0078 plus 4 times 1.0087 minus 7.0160. Next, we calculate the binding energy by multiplying the mass defect by 931.5 mega-electron volts. This gives us the binding energy of the nucleus. Question 2. Find the half-life if 75% of a radioactive sample decays in 6 hours. Solution. From the decay law, n equals n0 times e to the power of negative lambda t, 1/4 equals e to the power of negative lambda times 6, which implies lambda equals the natural logarithm of 4 divided by 6. The half-life, t1/2, equals 0.693 divided by lambda. 1. Derive the relation. 2. Explain the process of nuclear fission and fusion with energy release. 3. Write the properties of nuclear forces. 4. Discuss applications of radioisotopes in medicine and industry. And 5. Explain mass defect and binding energy with examples. Nuclear reactor schematic. Graph of radioactive decay, N versus T, fusion reactions in stars, fission chain reaction. Memorize important formulas and conversions, such as 1 AMU equals 931.5 MeV. Practice numericals daily. Write precise definitions and label diagrams neatly. Solve previous year question papers. Stay calm and manage time effectively during the exam.